Hello and welcome. Today I am going to solve these questions via numerical methods implemented on an online IDE called Octave Online using MATLAB code. The first question is asking to find the root of this polynomial function. What is meant by a root? Well, it's simply the point where this function intercepts the x-axis, or when this function equals 0. Newton-Raphson's method is what you call an open method. This basically means that the method to finding this root starts with an initial point, not an interval. So we pick any point between these two, for example 3.9. So how does Newton-Raphson method work exactly? Well, it gets closer approximations to the root using this function iteratively, this function. And what happens exactly is that we get the slope at the starting point that we picked, 3.9, and then approximating that function, and then using that to get the x-intercept of the tangent line. Displayed here is the code, and it's obvious that the answer reaches 3.0003 exactly. And here is the plotted function. And here is the flowchart. We clear the console, we write our function in x, and then we enter the iteration, the input, and the derivative, the starting point and the derivative. And then we iterate with the number of iterations until 5 iterations. Alright, to solve this next problem, we need to have a basic understanding of how the Taylor series method works. The Taylor series is just an expansion of this formula. It's a summation of derivatives to the power of 1 and then to the power of 0 and then to the power of 1 and then to the power of 2 and so on. You can add however many terms as you would like, divided by a factorial times a constant to the power of n. And this is how you would expand this kind of function. The idea of Taylor series is that it takes non-polynomial functions, such as exponential functions or sine and cosine functions, and we approximate them near some input. So for example, this question that we have, the initial value input is at x equals 0, and we use it to find y at x equal 0.1, 0.2, 0.3, 0.4, 0.5, so it's very close to the 0. So we need at least 1 decimal point of accuracy. And the steps to finding the Taylor series, there are 3 basic steps. First, you calculate the derivatives, and then you evaluate the function itself and its derivatives at x equal a. And then you fill in the right-hand side of the Taylor series expression using the Taylor formula. So if you would imagine that yn, or y, the function itself, equals this. If we have the first derivative, the second derivative that we can get from the first derivative, and the third that we can get from the second, well, we can just plug this in on the right side and find the y. So it's y equals this whole thing. And this is our code. How it works is that we iterate for I equal 1, which is the x, and then for with the difference, which is 0.1. As we established, it's 0.1 difference, it's 0 and then 0.1, and we iterate 5 times until 0.5. We find the derivatives each time, and we divide by the factorial, and then we output when the function... I need to see the clock. Okay, so confirming our code, we have also input the actual function solved analytically, which comes out to y equals e to the power of negative x squared over 2. And we notice that our output y values are correct to at least the 4th decimal point. And here is our flowchart detailing how our code works. In the final question, we solve a differential equation using Runge-Kutta's method. Runge-Kutta's method is also another method to solve ODEs. We use it Runge-Kutta method works by finding three slopes and summing them as if they were average. The three slopes have different values of x and y incremented by steps. The y is incremented by a step size proven from the function of the slope itself, i.e. the same function that we showed in the very first code, this one. The reason this is a good alternative method to the Taylor series method in the last question is that this formula for finding the y accounts for the most accurate slope and uses all the slopes k1, k2, and k3. However, if you look closely at the question given, we don't have the y function, so we must use the k1 derivative as the slope to find k2. The k1 derivative as the slope to find k2 here. And the k1 and the k2 and the k1 and k2 derivatives to find k3. So here is our code and our answer. It's just the y's and the f's. And here is the flowchart. K1, K2, and K dash. We calculate K1, K2, K3, and K1, K dash, K1 dash, K2 dash, K3 dash. And finally, here is the Excel sheet detailing the answer. So here is our code, here is the output answer, and here is the Excel sheet showing in details. Okay, here is the Runge-Kutta flowchart.